Alright, so now that we have introduced the idea of the atomic theory, as well as looked at the structure of atoms themselves, what we're going to do now is we're going to generate the link that connects atoms to the elements. Okay, so one important property of a given element is called the atomic number, which is usually symbolized by the letter Z. Okay, an atomic number is simply the number of protons in an atom. Okay, so every single element will have its own distinct number of protons. Okay, so for example, if you look at hydrogen, for hydrogen, Z is equal to 1. And if you look at the periodic table, you'll notice that hydrogen has a little 1 next to it, and that 1 is the atomic number. For helium, the atomic number is equal to 2. Lithium, it's equal to 3. Okay, so every single element from 1 all the way up to 118 has its own unique number of protons. Which means that if you know the atomic number of the element, then you can figure out what the element is. So, for example, the element that has an atomic number equal to 6, okay, is going to be carbon. And again, we can look at the periodic table to figure that out. Okay, another important property of an atom is going to be what's called its mass number. And the mass number is typically abbreviated as the letter A. And the mass number is equal to the number of protons plus the number of neutrons in an atom. Which means that if we know both the mass number and the atomic number for an atom, we can figure out both the number of protons and the number of neutrons. Now, when we are symbolizing an element, or we're trying to symbolize a particular atom of an element, usually we show the chemical symbol, and then we put in the mass number as a superscript in the top left-hand corner, and we put the atomic number as a subscript in the bottom left-hand corner. Okay, so if I'm given a symbol with this information, that's all I need to figure out the number of protons and the number of neutrons. So, for example, if we consider hydrogen, okay, we know that hydrogen has a atomic number of 1, and for some versions of hydrogen, in some hydrogen atoms, the mass number is also 1, which tells us that we have 1 proton, and if the mass number is 1, that means the number of neutrons is going to be equal to 0. Okay, remembering the number of protons plus the number of neutrons has to equal that mass number. Okay, there are other hydrogen atoms out there that look like this, where we have, again, 1 proton. And of course, it has to have 1 proton, because if it didn't, it wouldn't be hydrogen. And the number of neutrons would be equal to 1 as well. Okay, and there's yet a third type of hydrogen, which has a mass number of 3, and again, an atomic number of 1. So we have 1 proton and 2 neutrons. Okay, these 3 versions of hydrogen are what we call isotopes. Okay, so if you know the atomic number for an element, then you know its identity. If you know the the mass number of the element or the atom, then you know which isotope that you're dealing with. In fact, sometimes these are further abbreviated because if I put down the chemical symbol H, that's already implying that there's one proton there. So we don't always show that atomic number. Sometimes we just put the mass number, like we see here. Okay, now these different isotopes of hydrogen are abundant in nature in a variety of, at various levels. In other words, the first one here that has the mass number of 1 is what we call protium. Okay, it has also the name hydrogen 1. Okay, and then we have deuterium, which is hydrogen 2. And then we have tritium, which is called hydrogen 3. Okay, now what's the difference between these? Well, first of all, the most common isotope of hydrogen by far is protium. Okay, and that's pretty much about, I guess, 95% or so, or 97% of all the hydrogen in the world is protium. Okay, a smaller fraction is going to be deuterium, and the smallest is going to be the tritium, which turns out to be a good thing because tritium is radioactive. Okay, so that's the big difference between the isotopes, is that some of them are going to be unstable. Okay, and they also have significantly different masses. If you compare tritium to protium, tritium has 3 times the mass of protium, and that affects the way that it behaves. Okay, so let's look at another example, a different element that has multiple isotopes that are in nature. Let's say carbon. Okay, again, there are 3 very common isotopes of carbon. Okay, they're all going to have 6 protons, so they all have an atomic number of 6. Okay, and the 3 different versions have mass numbers of 12, 13, and 14. Now, in all 3 cases, the number of protons is going to be the same, because that's what makes carbon carbon, the fact that it has 6 protons. Okay, where they differ is going to be in the number of neutrons. Okay, we can see here that if we have a mass number of 12, there must have been 6 neutrons. If we had a mass number of 13, there must have been 7 neutrons. And if it's 14, you must have had 8 neutrons. Okay, and again here you can see that the first isotope that I've drawn here is going to be the most stable, and therefore it's also the most prominent in nature. Carbon-14 is actually radioactive, and accordingly there's not as much of it in the environment. Now again, just like we did before, we could abbreviate the symbol, keeping in mind that the atomic number is actually redundant for the symbol itself. So we could have expressed each one of these like this, just putting the mass numbers in. Okay, but we also have names that we can use. So this is carbon-12. Then we have carbon-13 and carbon-14. Okay, and there aren't any fancy names that we've given the isotopes of carbon. But this is how we can use the chemical symbol, along with its mass number and atomic number, to start to figure out the structure, or at least the how many of each type of particle are present in a given atom.